Alright, so recall that I had asked you to find out that given a T from V to W, I had asked you to look at that range of T, alright, is a subspace of W, and null space of T is a subspace of V, alright. T is a linear transform that is given to me. So, let us take some examples to compute them. I hope you have computed, you have tried it out yourself. So, let me take examples here to construct them, so that you understand what exactly we are doing. Examples 1, alright. Suppose I have given you f from R3 to R4 given by f of x, y, z as x minus y plus z, y minus z, x, 2x minus 5y plus 5z. I give you this. So, this is same thing as looking at this matrix 1 minus 1 1 0 0 1 minus 1 0 1 0 0 0 2 sorry anyway just a minute 2 minus 5 5, there is only 3 components here times x y z, alright. So, I have got a matrix which is 4 cross 3, and therefore, I am able to go from R3 to R4. Is that okay? So, if you want to find the null space of T, so if I write this matrix as A, null space of T is nothing but all x belonging to R3 such that T of x is 0, which is same as all x belonging to R3 such that Ax is 0. Alright, so this is same as null space of A, and we had already computed it, so we do not have to worry about. Range of T is same as Tx such that x belongs to R3. This by definition, if I look at here, is Ax such that x belongs to R3, and my matrix multiplication tells me that Ax is nothing but column space of A. So, we had already done these two in the previous class, alright, one of the previous classes, where we looked at the fundamental theorem of linear algebra, and they were the fundamental spaces, fine. So, I would like you to try them out yourself and get your answers, fine. Example 2, define T from Rx to Rx by T of f of x is equal to x f x, fine. I define this. What is null space of this? So, null space of T is, look at this, all polynomial f of x belonging to Rx such that T of x, so T of f of x is 0. So, it is 0 as a polynomial, 0 polynomial, fine. So, this is same as all f x belonging to Rx such that x f x is 0, and this is true only of the 0 polynomial. So, it is just the 0 polynomial for you, fine. What about the range of T is x f x such that f of x belongs to Rx. I did not write the first line, that is Tx part. So, as such it is supposed to be T of f of x belonging to Rx, fine. But here if I see whatever I do, x is a factor of this polynomial. So, when I say that x is a factor, by remainder theorem x minus 0 is there. So, it is nothing but collection of all polynomials f such that f is 0, f of 0 is 0. So, it is all polynomial f such that f0 is 0. So, I should have written the other way around, fx belonging to Rx such that f0 is 0. So, this is this collection, fine. So, you can compute them for different examples and learn yourself. So, now let me prove this very important result, fine. I would also like you to understand this, which I had said, but I did not write it down, that if T is from V to W, then dimension of null space of T is less than or equal to dimension of V. So, I am assuming that dimension of V and dimension of W are finite. Fine. I am assuming they are finite here, and therefore I can talk of these things. Dimension of null space of T is less than or equal to dimension of V, and dimension of range of T is less than or equal to dimension of W. I cannot go beyond W anyway, fine, because it has to go, the images have to be inside the codomain itself, fine. So you can prove yourself. This theorem is very, very important. This is what I was trying to say. So let us look at this definition. So let T be from V to W be a linear transformation. V and W are vector spaces, fine. I will take them to be finite dimensional for once and for all, always finite dimensional, and they are vector spaces over the same set, a scalar set. Is that okay? Then what happens is, the first thing, if S is a subset of V is linearly dependent, then T of S, so which is same as the set T of V1 till V of K whenever S is equal to V1, V2, Vk, then this is linearly dependent. So what I am saying is that any linear transformation, so we are saying that any linear transformation sends linearly dependent set to linearly dependent set. Is that okay? I do not have a choice here, fine. Sends dependent to dependent, fine. Second, so let S be a subset of V. Suppose T of S is linearly independent subset of W, all right. Ts is an element of the range, is an element, so I am looking at linearly independent subset of W, then S is linearly independent. So what we are saying here is that pre-image of linearly independent set is linearly independent, fine. This is very important. So any linear transformation sends dependent to dependent, and if I have got something in the codomain as linearly independent, it brings back linearly independent. Is that okay? So let us prove the two things, proof, fine. So let S is equal to V1, V2, Vk be a linearly dependent set, fine. Now, since this is linearly dependent, it means what? This implies the system alpha 1 V1 plus alpha 2 V2 plus alpha k Vk, the system this in the unknowns alpha 1, alpha 2, alpha k has a non-trivial solution, all right, fine. So this condition was very important for linear dependence. That was the definition of linear dependence, that something is linearly dependent means the system, this system will have a non-trivial solution, fine. Now since this has a non-trivial solution, just apply T to it both the sides. So I will get 0 is equal to T of 0. Every 0 vector is sent to the 0 vector itself under any linear transformation, which is same as T of alpha 1 V1 plus alpha 2 V2 plus alpha k Vk, and by linearity I can write it as alpha times T of V1 plus alpha 2 times T of V2 plus alpha k times T of Vk, all right. So, I am looking at this part now. So, what we know is that there is a non-trivial solution. The same non-trivial solution here gives you 0, all right. The same non-trivial solution gives a solution of the system star, all right. Hence, T of V1 till T of Vk is linearly dependent. So, let us understand again. I have a linearly dependent set. It means that if I look at this system, all right, the system that I am supposed to form to understand whether independent or dependent. So, that has a non-trivial solution. I know, so alpha 1, alpha 2, alpha k, some of them are non-zero. I know there are some of them are non-zero. From there, I go to the next step. So, from this system, I want to look at another system in which the vectors have changed, unknowns are still the same. Alpha 1, alpha 2, alpha k are still the unknowns, the vectors have changed. So, in the new system, I see that the same alpha i's which were the solutions at the earlier stage is still a solution to give me 0, fine, and hence everything is fine was. Is that okay? So, the idea here is again, see very nicely that we are just writing, earlier we had 0 was V1 to Vk, alpha 1 to alpha k, this was our 0. We already had a solution here for non-zero, so non-trivial solution. Similarly, again we are doing T of V1 till T of Vk and this. Okay. The important thing was that T of 0 was 0 itself. So, the same thing will give you, fine. So, how do you go back? So, understand that when you want to solve a system, you look at this part, fine. This is a system you would like to construct to show that T of V1, T of V2, T of Vk is linearly independent. So, you have to consider the system summation alpha I T of Vi I equal to 1 to k equal to 0 in the unknowns alpha 1 to alpha k. This is what you need to consider, fine. This will lead you to this part, fine, and I know that this has a solution because of this previous part. So, this will give me 0 here. So, this vector will give me 0 here and therefore, I will get that. Is that okay? So, you are not doing it directly, you are going it indirectly. So, understand it nicely. I wrote it like this, but the idea behind it that you look at this system, proceed, use linear transformation to go back here. From here, I know that there is a choice of alpha i's, there is a choice of alpha i's which gives me 0. Put that choice alphas to get 0 and therefore, you get a 0. Is that okay? The same alpha i's help you. The second one, the second theorem was that if, so I have been given that suppose S is some set which is V1, V2, Vn is a subset of V, and I have been given that T of V1, T of V2, T of Vn, this a subset of W is linearly independent. This is given to me. I have to show S is linearly independent. Fine. So, again, since I have to look at linear independence dependence, I will have to look at the system of equations. So, again look at the system of equation. So, form the system alpha 1 V1 plus alpha 2 V2 plus alpha n Vn is equal to 0 in the unknowns alpha 1, alpha 2, alpha n. So, look at this system, form this system, all right. Here I do not know the values of alpha i's, I am supposed to find those values, all right. But now I can apply t to it, fine. So, apply t on the given vector. on the given system. All right. So, if I apply t on the given system, what I get is that t of alpha 1 v 1 till alpha n v n is t of 0, which is 0. 0 is sent to 0, but this is also equal to alpha times t of v 1, alpha 1 times this plus alpha 2 times t of v 2 plus alpha n t of v n. All right. So, from this system, now I am going to this system. All right. In the previous example, we started with this system and went here, the other way around. All right. Here now I am looking at, I am starting with this system and then going to this system. Is that okay? Now, if I look at this system, so the system alpha 1 t of v 1 till alpha n t of v n is equal to 0 has only the trivial solution. Why? Why does it have only the trivial solution? Because we have been given that this is linearly independent because of this linear independence here. Is that okay? So, this set is linearly independent, therefore, this has only the trivial solution. So, therefore, this will have only the trivial solution, and therefore, we have that this set is linearly independent. Is that okay? So, that is what it is. Understand it nicely, spend some time, there is nothing special, but at least you should understand that any linear transformation picks dependent sets to dependent sets, sends dependent to dependent, and it takes its pre-image. So, if something in the codomain is independent, the pre-image will also be independent. All right. With this idea, you have this theorem. I will not prove it because the same idea was used in the previous part also, what is called the Rank-Nullity theorem. So, V and W finite dimensional vector spaces over F, T from V to W a linear transformation, then rank of T plus nullity of T is equal to dimension of domain, which is same thing as saying that range of T, look at this dimension of this plus dimension of null space of T is equal to dimension of V. Is that okay? So, we proved it earlier, same proof. So, the idea though I will just write the proof here. All right. So, look at nullity of T, null space. So, let dimension of this is equal to K, implies you have U1, U2, UK basis of null space of T, fine. This is a subset of V. So, I can extend it to form a basis of, so extend it. So, what we know is that every linearly independent set can be extended to form a basis. Here it is finite dimensional, that is very, very important. So, we are saying that extend it to get a basis U1, U2, UK plus 1 to UN, get a basis this of V. Is that okay? What we know is that range of T is generated by linear span of T of U1, T of U2, T of UK, T of UK plus 1, so on till T of UN. This is important. Range of T is generated by the linear span of the images. All right. This is what the first idea was. Fine. So, this is same as linear span of T of UK plus 1, T of UK plus 2 till T of UN. The rest of them, these are 0 vectors, so they do not give us anything. and then again go back, use those some ideas that you need to prove that this is linearly independent. So to show linear independence, try that out yourself. Just follow those things, you will get the answer. I don't want to waste my time there. Fine. Or you can look at the notes, the transcripts, where the proofs will be given. All right. So try it out yourself. I am not going to do that. The next idea is what is called, when do we say? So question. So if you remember, we used to have a function f from any set A to any set B. When do we say that f is 1, 1 and f is on 2? All right, fine. So similarly here also you can use the Rank-Nullity theorem to say some things. So let's look at some corollary of that. So again I am assuming these things are finite dimensional, phi to w, fine. Is that okay? So T is from V to W, VW finite dimensional, So 1, T is 1, 1 if and only if null space of T is the 0 vector. So let's look at the proof of this proof. Suppose T is 1, 1. So what was 1, 1? 1, 1 means that whenever fx is equal to f of y, then I must have x is equal to y. All right. So the idea here was, so suppose so T is 1, 1 means whenever T of x is equal to T of y, we must have x is equal to y. All right, fine. So let's look at the Tx is equal to Ty. So let's rewrite it. So since it is a linear transformation, therefore I would like to use that idea. So Tx minus T of y is 0. This implies that, sorry, so this is what it is. So I have to show null space of T or the kernel of T is the 0 vector. I have to show this. All right. So let x belongs to null space of T. This implies T of x is 0. That's the definition. So I am assuming that T is 1, 1. So this is what the definition of 1, 1 means, that whenever Tx is equal to T of y, we must have x is equal to y. Fine. We want to show that T is 1, 1 implies null space of T is 0. So take any x belonging to the null space of T. By definition of null space, T of x is 0, but I know that 0 is always equal to T of 0. All right. The 0 vector of the domain is sent to 0 vector. So what we see here is that this part is telling me that T of x is equal to T of 0, and therefore here I can apply T is 1, 1 to get that x is equal to 0. All right. Look at this definition part here. Whenever Tx is equal to T of 0, x must be equal to 0. Fine. So we have shown that null space of T contains only the 0 vector. All right. You have taken any x in the null space. So by definition of null space, this is 0 because the definition of null space. This is there because of T is linear transformation, and now this part gives you that, and with T is 1, 1 gives you that x is 0. Is that okay? The other way around now. So assume null space of T is 0. Assume null space of T is 0 to show T is 1, 1. So assume, so let T of x is equal to T of y. I need to show that x is equal to y. So this part gives me T of x minus T of y is 0. This will gives me that T of x minus y is 0. This gives me that x minus y belongs to null space of T, but null space of T is just the 0 vector. All right. So this together will imply that x minus y belongs to this set and which is same thing as saying that x is equal to y. Fine. So, we have shown that T is 1 1 if and only if null space of T is 0. Fine. The next thing we would like to look at what happens to onto. When can I say it is onto? So, when is T onto? So, I have T from V to W. Fine. What we know is that if I look at T, fine, I need to look at T of V1 till T of Vk, this, where V1, V2, Vk, this is a basis of V. So, where if I have basis here, I have to look at this. So, this gives me range of T as linear span of this set. Is that okay? If I want onto, so onto will imply that range of T should be equal to W. Dimension of range of T should be equal to dimension of W, or implies that, can I say from here, so if I look at here, so I can say that dimension of range of T is less than equal to dimension of, can I say this? What we have seen is that V1 to Vk are linearly independent, need not imply that this is linearly independent, need not imply linear independence, all right. If it does not have linearly independence, the dimension of this will be less than equal to k, and what was k? K was the dimension of V, all right. So, therefore, this is true, and hence I can think of onto. So, onto comes into play only if dimension of W is less than equal to dimension of V. Is that okay? As such, I cannot guarantee anything, I can only say this. Fine. So, there is this corollary. All right, I will just write the corollary, that let T from V to V be a linear transformation, then T is 1 1 if and only if T is onto, if and only if null space of T is the 0 vector, all right. So, look at this, we have already shown that T is 1 1 implies this part, I have already shown this part. This part we will to use this idea of dimension. So, for us T is onto will imply that both are V itself. So, this will imply that linear span of T V1 till D Vk should be equal to linear span of V1 to Vk, which is your V itself. So, what we are saying is that from V1 to Vk I am going to T V1 to T Vk. So, in some sense we are saying that T is invertible. I have not yet defined what do I mean by a function being invertible, that you already know when is the function f is 1 1 and onto, fine. As soon as you have said that these are linearly independent, you get that null space is 0 because of the Rank-Nullity theorem, which says that if this has dimension n, this has dimension n, so this will have dimension 0. Is that okay? Fine. So, the Rank-Nullity theorem tells you that this will itself be valid, all right. So, this part, looking at this part, is coming from the Rank-Nullity theorem. Is that okay? So, I will end here. In the next lecture, we will look at what are called isomorphisms and so on, and relate these ideas, fine. So, that is all for now.